today I would like to talk about functional topological antiferromagnet, manganese-3 tin. Maybe then I will include family compounds such as manganese-3 germanium. So my name is Yoshichika Otani, and I'm representing Institute for Solid-State Physics, the University of Tokyo. Sorry, just I'm going to use a laser pointer. And also at the same time, then I have a research team in Center for Emergent Matter Science in Riken. So then today, my talk is fourfold. I begin with introduction. And we are talking about this non-collinear antiferromagnet, which has a function as a spin source. And also I would like to emphasize a function as an information storage. So that means that this material that it has a time reversal symmetry is broken. And I'll summarize my talk. So the first one is this introduction. To begin with, I'd like to just introduce my collaborators. And you can see in my studies that I have collaborated. This guy, the ex-my student, and also ex-my assistant professor in my group, my senior researcher in Riken, and also the other physics department colleagues, and also the other applied physics department colleagues, and also university electrical communications. They helped us a lot. And then as a result, and we've got several papers about the topics about related to antiferromagnet, non-collinear antiferromagnet. If you're interested in that, please visit these papers. This is just funding bodies. So I'd like to just mention, we use spin Hall effect, which is a bulk effect. As you know, the 4D or 5D transition metals with strong spin orbit coupling, such as platinum, tantalum, and tungsten, and also doping copper with iridium or heavy metal bismuth, we can get a large so-called spin Hall angle. That is a ratio how much spin current can be extracted from charge current. Nowadays, then, which ranges from 5 to up to 30% or so. But still, then I'd like to have something efficient conversion and also new functionality. So the recent trend is something like to use interface or surface. Topological insulator surface state will give you, in principle, 100% of spin conversion. More recently, then we are just focusing on antiferromagnet, which has a function of spin source, as well as information storage. So that's what I would like to say. If you look at, as you may know, everything, the antiferromagnet, if you compare the function of antiferromagnet with ferromagnet, which has nearly zero stray field due to the compensated saturation magnetization. And also then which is very good for miniaturization. And secondary resonance frequency, ferromagnet shows something like the gigahertz range. But in the case of antiferromagnet, you can find sub-terahertz very, very fast. So that's why then we can expect high-speed operation for application. And also material-wise, in the case of ferromagnet, to find the room temperature semiconductor is challenging. However, if you look at antiferromagnet, it's available. So that means a variety of material choice. But this coupling with magnetic field is kind of important issue. You see antiferromagnet, the fully compensated magnetization, that's why this is indirect and it's very difficult to control. So that's why then we want to have something functional antiferromagnet. You see, then if you look at the ferromagnet, you know the magnetization curve, hysteresis, response is huge. So that then we can get non-volatile memory function and some electric devices such as anomalous Nernst effect-based devices. And also magneto-optical response is also huge. And then we can utilize this one for imaging. So in the case of antiferromagnet, as I said, magnetization is almost compensated. That's why there's a rule of thumb that we cannot expect any response. So that's why even Nobel laureate Linnell said that this antiferromagnet is useless. So that's why we are seeking the kind of functional antiferromagnet which shows large magnetic response, as you can see here. You see that then we would like to just introduce this manganese-3 tin. Recently, this material is popular. There are lots of researchers who are studying on this. And the crystal structure is something like this, stacking triangular lattice structure. And if you look at from the top, You can see this kind of typical Kagome lattice, and a spin is located in this way. And if you look at only one set of spin in this region, which actually breaking the time reversal symmetry is broken. You see that when you apply magnetic field, this spin is slightly tilted, which creates extremely small, vanishingly small magnetization, so that then you can manipulate this spin structure by applying external field like this. You see, if you flip the magnetic field direction, then you can flip. So that means, in principle, this what we call octupole behaves like a macro spin. So that's what is a very important message. And this small magnetization ranging something like 0.05 millieV per function formula unit. This is a Canting orbital moment. Small in plane anisotropy energy. And then I'd like to say, emphasize that Antiferromagnetic domains breaks the global time reversal symmetry, can be controlled by the in-plane magnetic field. Now, then I'd like to just get into the function as a spin source. As I said, this sample, this material, non-collinear antiferromagnet, magnitude 10, it's a non-collinear antiferromagnet with nail temperature of about 430 K, which has a hexagonal nickel-3 tin type structure with space group P63 MMC. And it looks like this stacking structure. And if you look at the top, and this layered structure forms Kagome lattice, and this is a kind of representative picture. And when you apply magnetic field, and as I said, in a Canting moment, which you create a very small magnetic moment, net magnetization. If you just apply this small magnetization per manganese atom, and you can expect from this empirical relationship, the response is extremely small. However, in reality, then in 2015, Professor Nakatsuchi's group found huge response in anomalous Hall effect, as you can see here, at room temperature. You see, so that's why they studied a lot the origin of this behavior. And they found large anomalous Hall effect, which is due to the fictitious field of 200 Tesla, which is originating from the belly phase, which exert on the moving conduction electrons. This is the distinctive nature of wild antiferromagnet. In fact, this materials can be classified as a wild antiferromagnet. There are lots of studies and bound calculation performed by Professor Arita's group in collaboration with Professor Suzuki and also Koretsune in Tohoku University now. And they found this they did a mapping of location of the wild nodes, wild points like this. And then this was confirmed by the RPS measurement, as you can see here. Although this distribution has to be stretched, this relationship between the two is a bit different. But basically, then this structure was confirmed by RPS measurement. So it's a very important message. As I already said, this cluster octupole behaves like a macro spin, which can be controlled by external field. You see, like this. At the same time, when we apply and then when we change the location, and this octupole also rotates in this, as you can see here. This is a very, very distinctive feature of this material. So what we can just conclude or say from these experiments is a switching of cluster magnetic octupole, this one. Octupole moment decides the fictitious field direction. Cluster magnetic octupole breaks time reversal symmetry. That's why I said that this behaves like a macro spin. So this makes our life much more interesting, research life much more interesting by using this material, belly phase, and also this wire points, which create an fictitious field, which allows us to probably test this non-volatile, you see, memory function, and also magneto-optical behavior is already examined by Hiko et al. in 2018. As you can see now, then we can just observe this kind of domain evolution by optical means easily. And also some electric response was already being demonstrated by one of the students in University of Tokyo, like by using this kind of a structure. And then that's why then we can say the large responses become available for antiferromagnets. So what we are interested in, and as we have been working on the non-local spin bulbs and the spin accumulation, if there is such a huge anomalous Hall effect, then we can automatically expect spin accumulation in the surface region as a result of anomalous Hall effect. That's what we thought at the starting point. And then we started to measure by putting ferromagnetic electrode, and which is aligned with this kappa electrode, and which is perfectly orthogonal to the current direction. So that then we can expect, if we can just measure the chemical potential, we can see this kind of hysteretic behavior by using this. All the sample was fabricated by using FIB method, and lithography allows us to set the electrode like this, and we did experiments. So this, surprisingly, as we expected, in the hysteretic response was observed here. And the surprising thing is, if we just flip the spin structure by flipping the external magnetic field without changing the ferromagnet, okay? So then there is now response of the chemical potential by measuring this soft permanently electrode. We can get already completely flipped hysteretic response. So that means a sign reversal of spin accumulation when this octupole moment switches. That's what we found. This is surprising that this kind of response could have not been controlled by external field in the case of ordinary spin Hall effect. You see, and then we started to collaborate with Professor Chen and also Professor McDonald's group, and we found, compared with conventional spin Hall effect, magnetic spin Hall effect exists in this material, which response is somehow controlled by the magnetization direction with respect to the current direction. At the moment, our geometry is something like this. So that's why then we can expect perpendicularly aligned spin accumulation like this. And also then we did confirm, in order to confirm this type of response, we did angular dependence of spin accumulation was measured by STT, spin transfer torque measurement. And by this, the calculation showed this kind of you see variation when you change the magnetization octupole direction, as you can see in this cartoon, the animation. You see the X and also Y and Z component. This one is a Kagome plane. Interesting thing is spin accumulation vector seems to rotate in this light blue disk. So that means octupole direction can be controlled, and then the spin accumulation vector sometimes, and if it goes out of plane, it's tilted a bit. So that means that this is very beneficial for us, and if we can utilize this spin accumulation. So then we did an STFMR measurement to see whether this effect is can be observed by this behavior. And then we found exactly the same type of response. And more importantly, this field-like torque and also spin transfer torque contribution is huge, even with is compared with the platinum, beta tantalum, or beta tungsten. This just reaches something like a 70 or 80%. So this is a very, very surprising feature of this material. So that's what I can just propose is, we haven't demonstrated yet, but in the case of platinum tantalum, and you can use, you see, charge current, and which create the spin accumulation at the surface, and which drives the spin current in this way, and then you can just, you see, flip the magnetization. But in the case of magnet-free tin, we don't need to this kind of bias field, and which breaks the symmetry. But since this is already tilted spin accumulation allows us flip the magnetization by like this type of scenario. So that's what we have found in this. This is a kind of spin source functionality of this material. So then I'd like to move to the function as an information storage. You see, as I said, this cluster magnetic octupole behaves like a macro spin. And then you can just flip at will by applying small magnetic field like this. So macro spin, this octupole changes the direction by applying external field. Already based on this type of idea, there are theoretical study performed by Professor Balent's group in UC Santa Barbara. They found this type of nail wall-based domain structure could be stabilized in this material. At the same time, then if you remember that you can just take a c-axis of this material along the current direction, so that then you can have a kagome, stacking kagome plane like this. So in this case, then we can stabilize this in this material, the Bloch wall-like structure. So we say the Bloch-like wall because then this spin consists of magnetic octupole. So then our objective becomes that to clarify whether we can cluster magnetic octupole behaves like macro spin. That is already we see some evidence, and we wanted to see whether this is really true in this sample, and also to understand the antiferromagnetic domain wall structure. How does it look like? And thirdly, and we'd like to demonstrate the electric current driven antiferromagnetic domain wall motion. So that is what we are aiming at. To begin with, already electrical manipulation of wild antiferromagnetic state by using a spin orbit torque. You see this material coupled with heavy metals such as platinum, and we can switch magnetization octupole direction at will, back and forth. You see, and also the omnidirectional control of large electrical output in topological antiferromagnet is also available. That means even polycrystalline, then we can have a very interesting response. Omnidirectional, in any direction, then we can have a nice hysteresis loop is kept, and then we can have this kind of multi-level output. So that's what we can expect from this material. And then when we wanted to, we started to do the numerical calculation to visualize or to understand domain wall configuration by setting this type of wedge type of structure. And this one is a naturally drive domain wall to one direction. That's why in order to have a domain wall right perpendicular to, this is a cross-sectional view. Okay, size-wise, this one is something 0.67, 0.7 micrometer. And the length is about 0.5 micro, 1.77 micrometer or so. And this thickness of this material on left and right is slightly different. So then as a result, then we fix the boundary condition. This is up and this side is down. And we see this six-fold symmetry, which reflects on this type of different octupole direction. And then we just used a single crystal manganese tin and cut out this whole bar shape. And what we did was we sent a pulse to nucleate domain wall, possibly here. And then second pulse can be sent horizontally. And then eventually this is pinned, and then you can just drive only one of them towards the left-hand side. And then you can see this magnetic state of this side, so that then you can measure the speed of propagation speed of this domain wall. You see, and then we've got this type of velocity, which is given by the pulse duration, Yeah, velocity can be given. The duration, this length divided by the pulse duration is this, gives you some velocity as a function of current density, which shows something like this. And gradually, it's a background already, just because of heat, which excited the movement. But then if you look at very, very closely, analyze carefully, and we saw we see slight polarity-dependent behavior. This is actually the very, very small behavior, but assuming a linear scaling at conventional current regions, and this one is up to 10 to the 9th, that means 10 to the 10th. And if you extrapolate this one up to 10 to the 12th, and we can expect 50 meters per second. In fact, and it turned out afterwards, this is a creep regime. And recent experiments show this velocity goes up to 1,000 meters per second or so. So we believe this is getting into the flow regime. That's what we'd like to show you. So in order to clarify this, and we just made this kind of sample, which is kind of from the single crystal manganese-3. In this case, germanium, the slab, and manganese-3 tin as well. This kind of rod, and you just send this. There is a electrode here. It's not connected to this material, and we can send a pulse so that the L-state field is created, and we can nucleate domain wall here, and also at the same time here. Okay, so that's what we do. And then there is a horizontal current, secondly, and then which pushes domain wall and then moves. But the optical measurement is real demonstration in this type of measurement, and we can see nucleated domain wall with applied, you see, magnetic field perpendicular to the wire, and we can nucleate this magnetic octupole domain walls, two of them, a pair of them, and in this time, this region is pointing upwards out of this plane. And then the horizontal current is applied, and this one moves towards the right-hand side. And then another second pulse also pushes this domain towards the right-hand side. As you can imagine, in the case of magnetic field, this one is just a two domain walls split and then put by far with increasing the volume of reversed region. So that's what we found. So that's why the critical distinctive difference between the current-driven and field-driven magnetic octupole domain. So then we demonstrated current-driven MODW motion, magnetic octupole domain wall motion, and magnetic octupole domain wall starts to move by a current of 2.3 times 10 to the 9th ampere per meter squared with no magnetic field. This is very small value. So then we did a systematical measurement for Bloch wall type, Bloch type wall, and also nail type wall. Nail type means spins, rotates in the same Kagome plane. But in the case of Bloch wall, the Kagome plane is stuck in this way. So that is the difference between Bloch-like and a nail-like wall. Surprisingly, in the case of manganese-3 tin and also manganese-3 germanium, which shows a huge, you see, speed. In the case of manganese-3 germanium, which goes up to 750 meters per second or so, but which is much larger than the manganese-3 tin. Another interesting thing is nail wall moves much faster than the Bloch type wall. So then, as I said, on 750 meters per second, the current density is only 7.56 times 10 to the 10th ampere per meter squared. Additionally, without no magnetic field. And also, this region corresponds to what we have already observed in the previous study. And this exhibits creep motion under low J regime here, and a flow motion regime under high J regime. So it's above 3 times 10 to the 10th ampere per meter squared. So this is same feature can be observed in the case of manganese-3 tin. So, and also then what we like to say is we are proposing that non-equilibrium spin accumulation, which arises in the vicinity of domain wall, which is maybe the responsible for this domain wall motion. That's what we are thinking at the moment. And also then if we just summarize domain wall mobility as a function of magnetization, which shows like this. So ferromagnet, this one is a ferrimagnet. Also then we mix all this SOT measurement as well. But the tendency domain wall speed is much faster than any other magnetic materials in terms of this domain wall mobility. And also JC, that means a critical current density, and if it's necessary to drive domain wall, is also very small compared with other materials. That's what I like to just mention. So this is what I said, just summarizing. Okay, I think then I'd like to just, I have talked reasonably a lot, and then I'd like to summarize. We found a new class of non-collinear antiferromagnet, manganese 3X, that's including manganese 3 tin and also germanium, which exert large responses, as in the ferromagnet materials, in which cluster magnetic octupole determine the fictitious field direction. Antiferromagnet domain wall evolution in non-collinear antiferromagnets, manganese 3X, and we studied and then we found which moves in the creep motion, 50 meters per second. But now this type of study by using a magnet optical method, and which shows we can just reach much larger speed, close to the 1,000 per meter, 750 meter per second or so. So thank you very much for your kind attention.